10 years ago.
We encountered one of the worst vulnerabilities in human history. During that time, I was just starting my career as a system administrator, and I asked myself a question back then. How is it possible for anyone in the internet to exploit this easily? I finally got the chance to answer it. I know this is an old vulnerability, and there are a lot of exploits developed over the years, but I want to go back and answer some of my questions before. And I want to take my knowledge of TLS protocol to the next level. Reading the existing exploits didn't help me that much, so I created my exploit from scratch. During the process, I learned a lot of important details that we don't normally learn at school or at work. These are the things I want to share to you in this video. In order to gain full understanding of the exploit, we will first analyze the vulnerability. Then we will start constructing the code and solve any issues we encounter during the process. Heartbleed is a vulnerability on OpenSSL that allows anyone from the internet to read data from the server's memory. This allows bad actors to get whatever sensitive data present at the time of the attack. OpenSSL is a popular tool that implements SSL and TLS protocols. Take note of the difference between protocol and implementations, as we will use these terms throughout the video. OpenSSL is more than just a command that we used when creating TLS certificates. At its core, it's a library which is used by a variety of applications. Older versions of OpenSSL implements the Heartbeat extension. Extensions are used to modify the behavior of the protocol or provide additional functionalities. Certain older OpenSSL versions are using Heartbeat extension and vulnerable to the bug. Heartbeat extension provides keep alive functionality between two ends. The client sends a heartbeat request message to the server. The structure of the message contains the following. Message type is set to 1 since this is a request. Next is the payload length, which is self-explanatory. Payload can be any random data the client wishes to send. Last will be the padding, which is another random content and needs to be at least 16 bytes. Once the server received the heartbeat request, it must respond back with a heartbeat message containing the exact payload the client sent him. Do note that both request and response use same message structure, but they use a different message type. These information are crucial in developing the exploit, so please be patient and pay attention. But don't worry, we will discuss these details again later when we develop our exploit. Now that we know how Heartbeat protocol works, let's discuss the vulnerability. I downloaded a vulnerable OpenSSL code on my Kali. Let's open the file which contains the code that is responsible for sending the heartbeat request. We are seeing a lot of lines here, but let's focus on the relevant parts only. This is the part where the heartbeat request is being prepared. The structure is just the same on what we discussed a few seconds ago. First is it allocates certain amount of memory space during runtime, 1 byte for the message type, 2 bytes for the payload length. Next is the actual payload. The last one is the padding, which is another 16 bytes random data. As of now, you won't see anything unusual. Code seems harmless. But let's see what happens when we take a peek on the code that provides the heartbeat response. It tries to do similar thing from the sender side by allocating same amount of memory. After that allocation is done, it returns a pointer and it stores it inside BP variable. Next is it stores the message type on the first byte. In this case, this will be hexadecimal 2 since this is a response. It then increments the pointer by another 1 byte. After moving to the next memory location, it uses a macro that serializes the payload length into a 2 byte memory space. After that operation, the pointer location moves 2 bytes ahead. Next is it copies the actual payload it received from the sender to the next pointer location. Memcopy uses a third parameter which tells it how much data it needs to copy. In this case, OpenSSL is telling it to copy a certain amount of payload length. The question is, how much is that amount? Looking further up, the amount of data or the payload length is determined in this line. Once it receives the heartbeat request from sender, it will get the memory location of that data. Then it will store it inside a pointer called P. It will first dereference the first byte of memory. In other words, it will get the content, which is the message type. After that, it will increment the pointer by 1 byte. The next step will be the process of extracting the payload length. It uses another macro which performs the inverse operation of what S2N macro does. In this case, it deserialized the 2 byte payload length it received from the sender. Look in a higher view of this code, we cannot see any statement that verifies the payload length we got from the sender. That means receiving a large payload length will result to a copy of unwanted data from the nearby memory region. This is where Heartbleed happens. In summary, in order to extract data from nearby memory regions, we need to send a heartbeat request with large payload length. Before we end this section, do note that accessing memory inside the server have limitations. A process or thread cannot access data from a memory allocated to another process. This means when we execute our exploit, we can only get data from memory assigned to the application running OpenSSL. Before we craft our exploit, we need to find a vulnerable application. Since we will be exploiting a very old version, setting this up from scratch will result in dependency issues because most apps no longer use this vulnerable version of OpenSSL. So to avoid headaches in setting up, we will use a Docker container. I found a nice image that we can use. That is empiric Heartbleed. I didn't really have a preference on what to use, so I just chose this image randomly. I'm already running this container on another machine, so let's access it. This is in Spanish, so let's translate and see what it says. The message is interesting, as this is what we commonly see on Capture the Flags. There is nothing much we can see here, so let's go to the terminal and start constructing our exploit. Like with my other scripts, I like preparing the base structure to give me a high-level overview on the flow, so let's do that. Let's import ArdParse since we need to pass command line parameters, and also initialize the options we need to pass to the script. We need the target IP as required parameter. The target port can be optional, but let's put a default value of 443. Since we will need to construct a heartbeat request, let's create a dedicated function for that. We'll just put a placeholder for now. Then once we construct that, we need to send it to the target. In order to do that, we need to use socket module to send raw bytes. After sending, we will get the response, print it, and close the socket. Looks straightforward and easy. Well, not really. When I'm initially constructing this exploit, I went to a bit of rabbit hole, unable to get a proper response from the target. So I tried to dig deeper into how the heartbeat protocol works. While reading the RFC protocol spec, I noticed this statement. A heartbeat message can arrive almost at any time during the lifetime of a connection. So does it mean there must be an established TLS connection first, before I send the heartbeat request? I then looked into the internals of the TLS connection and started creating the code that will perform the TLS handshake. I hit another hiccup on the client key exchange part. My code that generates the pre-master secret from server public key using ECDH is not working as expected. This cost me a bit of time again trying to make it work. Running out of ideas, I tried to look for a different approach. While looking for other ways, I tried to read again the different protocol spec and came across another statement. A heartbeat message should not be sent during handshakes. As per RFC requirement levels, should not means not recommended but may still be happen on some circumstances. So I got curious. What if this version of OpenSSL doesn't adhere to that rule? What if I can just send the heartbeat request right after the initial message? So I tried that, and I got my heartbeat response I've been waiting for. So that's the story why we cannot just send a heartbeat message without first initiating a TLS connection. And it also saved me time in making the full handshake process work, which is not really necessary. Some takeaways before we go back to coding. RFC protocol specs are rules and guidelines. There are parts that must be enforced, but some are not that mandatory. Some applications implement rules correctly, but some may not. And pay attention to the statements. They are crucial in understanding the protocol. Now, let's go back to our code. As we just discussed, we need to send first a client hello message before sending the heartbeat request. Before populating our client hello function, we first need to understand how the structure looks like. Throughout this video, I've been showing you snippets from RFC protocol spec. Not all are familiar with those long documents, and it may be confusing to some. So let's approach it differently this time. Instead of relying on them, let's go and check an actual packet capture in wireshark. I saved some TLS traffic capture previously, so let's go to that. Let's type TLS to filter the messages. What you see here is the entire TLS packet. It consists of different parts. If I drop this down, you will see the record layer. Within TLS itself, there are different protocols. The record layer encapsulates the different messages carried by these protocols. The handshake protocol is the one which most people are familiar with. But as we discussed earlier, we will not complete the full handshake as it is not necessary. Going back, if we drop this down again, we will see another set of data. Let's focus our attention on the next 3 lines. First is the content type, which is a handshake. Next is the version of the TLS being employed. In other words, this should be the same as the TLS version the client wants to use for the connection. Last is the length. Length is the amount of data below this layer. Later, when we create our function, we will need a strategy for getting this value. We also need to convert all these properties into bytes objects, so we will use a different method to do that. So in summary, these 3 properties is for the record layer and not for the actual handshake. Now let's check the handshake itself. This is the Client Hello handshake, which consists of multiple fields. First is the handshake type. Next is the length. This is the amount of data of all fields next to it. Third is the TLS version the client wants to use for the connection. This is the actual field the server will look at during negotiation. Notice that this is different from the record layer version we just discussed. Next is a 28-byte client random. Next 2 fields are for the session identifier. This is used when a connection needs to be resumed. Next is the list of cipher suites supported by the client. We will not discuss them, as we will not perform a full handshake. Last lines will be the compression methods and extensions. Extensions are the one we discussed on the first part of this video. One last thing. If you notice, there are 2 lengths here. First one is the length of the whole handshake protocol. Next is the length of the actual handshake fields and properties. So in order to get those values, our strategy would be construct the packet starting from the inside. Let's go back to our exploit. Let's first construct the inner fields of the handshake protocol. First is the version. We will put this into a constant since this will be reused throughout the code. Each version has its own hex code. For demonstration purposes, let's use SSL version 3. Major version first, then followed by minor version. Next will be the client random. This consists of a 4-byte Unix time representation and a 28 random data. For the first part, we will get the current time, then convert it into a floating number. Then we need to strip the decimal values. And finally convert it into 4-byte Big Endian representation. We need to convert it into Big Endian because that's what is used in network protocols like TCP/IP. After that, we will append the 28-byte random data. We can easily generate something using urandom function. Next field will be the length of session ID. It is 32-byte long, so we need to get the hex representation. We can easily get this using hex function. We just need to pass the integer. We can also use struct module to convert it into bytes object. But converting it in this manner can produce an alternative result. In this case, it produced a space because decimal 32 is also represented by space character. So to avoid confusion and to make it more obvious, let's use the result from hex function. The session ID itself is just a random 32-byte data, so let's just use again urandom function. The next 2 will be the cipher suite fields. Since we are not completing the handshake, this means the cipher suite has no real use since the negotiation phase will not happen. But we still need it in order to send a valid Client Hello packet. We can put any valid cipher suite data we want. One easy way is to just copy this from an existing packet capture. I already did that, but I'll show you a quick way to do it. Go to the packet capture, right-click on the field, copy it as a hex string. Open a Python interpreter and use the bytes from hex function. Repeat same step for other fields you want to copy. Let's do the same process for our exploit. Next will be the compression methods. As per my research, these are not widely used, but we need to specify them for completeness. Compression method length will be 1. And compression method will be 0, meaning it's disabled. The last fields for the handshake protocol will be the extensions. For my testing, the exploit works even though I remove other extensions. But I needed to keep one, which is the heartbeat extension, which makes sense because we are sending a heartbeat response. That means we can just copy this also from a sample packet capture. This is how it looks like in Wireshark. We will just use same process of copying it as a hex stream and converting into bytes object. Next is to get the length of that extension. If you notice, the length is easy to calculate. This is just 5 bytes. You might attempt to just put hex 05 as the value, or just use hex function to get the proper length. Both will arrive with similar answers, but there is an issue. Based from Wireshark, the length is stored in 2 bytes, but these values are only 1 byte. A good way to generate a 2-byte representation of length is to use struct module. That will also allow us to specify the proper byte order. This function is really useful, especially if you are dealing with long byte string. So far, you've seen different ways on how byte objects are being transformed in Python. This is important if you are serious in becoming an exploit developer. You need to understand what method to use and when to use them. Before moving on, let's import some of the modules we used. Now that we've finished constructing the fields on the inside part of the packet, let's group them into one variable so we can easily reuse them. Not sure what to call them, so let's just say handshake payload. All are in bytes objects, so we can just easily add them. Since this will be a very long statement, we can span them into multiple lines using backslash. To recap, we have constructed the inner fields of the handshake protocol. We got their length as well. We can now complete the handshake protocol by constructing the remaining 2 fields. Handshake type will be 1 since this is a client hello message. Next is the byte object representation of the length we gathered above. Notice this small x here. Wireshark is showing that it occupies 3 bytes, so we need to get the 3-byte representation of that length. H is 2 bytes only. In order to add 1 more byte, we need to use a padding. Then to complete the handshake protocol, we will just add those 3 parts all together. We are done with the most complicated part. Now let's construct the record layer. We first need the content type. I just copied this value directly from Wireshark. The next is the record layer version. Remember that sometimes this can be different to the client version inside the handshake protocol. For simplicity, let's just make sure this is the same all throughout the code. Next one is the length of the handshake protocol. This will be easy as we already had this constructed. In this case, it just needed a 2-byte representation, so let's just use struct module without an extra padding. Then adding all those 3 fields will be our whole record layer. Finally, we will return the record layer plus the handshake protocol. Before we move on to the next section, let's confirm first if our client hello packet is working properly. If this is working, we will expect multiple messages from the server, such as the server hello. Let's run the exploit. We'll pass the target hostname and port. Don't worry about the output for now. We will fix that later. Let's go to Wireshark. Looks like it's working as we expect it to be. We received the next messages in the TLS handshake. The client hello packet looks well crafted. We see here the SSL version 3, which is the one we specified in the exploit. Don't mind the errors. Errors like this will be normal since we are not following the entire protocol spec. The Heartbeat packet is much simpler than the client hello. Same with other TLS protocols. The Heartbeat message is also encapsulated within a record layer. Similar with previous approach, we will copy most of the fields from an example packet capture. Then we will return the packet consisting of the record layer and the Heartbeat message. Since this packet is much smaller, we don't need to start constructing from the inside to get the proper length of inner fields like what we did in the last section. The sizes are predictable and we can just manually specify them. So let's start on the outer part, which is the record layer. Content type will be hex 18, which indicates this is a heartbeat request. Client version will be the same on what we are using throughout the code. Length will be just decimal 3 and 2-byte representation. Then adding all those together will be our entire record layer. Now let's go to the heartbeat message. First is the message type, which will be 1 since this is a request. Next is where the vulnerability is triggered. This is the payload length, which tells the server how much data it should give back to us. To make this configurable, we will pass this as a command line parameter. The length should be transformed into a 2-byte representation. Notice that we used uppercase H instead of lowercase. Lowercase h is for signed short. That includes negative numbers, and the max number is only around 32,000. If we want to get the maximum possible data from the server, we need it to be around 65,000. And it doesn't make sense to specify a negative payload length. So to improve the exploit, we will use uppercase H for unsigned integers. Next is the payload content. This can be any 2-byte data. Notice that we didn't use a hex value here. This is another way of specifying byte objects in a more readable format than hex. Last will be the 16-byte random padding. Then to complete the heartbeat message, we will just add those fields all together. Now that we both have the functions needed to send the packets, the next thing we need to do is to print the response into something we can understand. Before that, don't forget to adjust the amount of data we want to receive from the socket. Let's make this the same as the payload length. Then we will need a special function that will decode the response. Let's call it print ASCII. We will pass this function the data we receive from the server. We can print the data in any way we want. So let's try to use the format of hex dump from wireshark. This is a bit hard to do, so let me explain first our strategy. The hex dump consists of two columns. The left side will be the hex representation of each byte. Right will be the ASCII representation. Since this will be two columns, it makes sense to use a two-dimensional array. We can do that by using a list of lists. The content of the first list will be the hex values. The second list will be the ASCII values. We need to specify the width of each column. Let's just use 16 for demonstration purposes. In order to start printing on the next line, we need a logic for that. And we also need to represent any non-printable characters as a dot. Now let's go back to our exploit. Let's initialize our two-dimensional array. Then let's set our width to 0. This will serve as our counter. We will increment it, and when it reaches 16, it will be the signal that the next output will appear on the next line. The buffer we pass into this function is a list of bytes object, so we will loop through each item. For each byte, we will get the hex representation. We can use Python f-strings. Next is we need to get the ASCII representation. We need a bit of code to do that. We will get the ASCII representation of the byte object. That will happen only if the character is one of the printable strings. Else, we will just display a dot. Once we get the hex and ASCII representation, we will store them on their respective list inside the two-dimensional array. We need to strip any white space from the ASCII characters to prevent misaligning our output. If our counter is still less than 16, we will do nothing but to increase it. At this point, we are not yet ready to print the output since we haven't reached the target width of our columns. If it reached 16, that is the time we will print our output. We will also reset the counter to 0 and clear the contents of the two-dimensional array. So if you get the logic, we are buffering the data inside these lists. We are trying to fill each list until they reach 16 items since that is the width of our columns. Once filled, we will flush the buffer and be ready for the next iteration. Thank you for joining me in this video. If you have questions, I urge you to ask, and I will try my best to answer it. Please comment it down below so others can see as well. Before we end, please support me and my channel by sharing this video to others. Again, thank you so much for joining me. See you on the next one.